Welcome back, guys. In this video tutorial I am going to discuss few important concepts on D block chemistry. So before moving on to the subjects, you need to understand where you put this D block chemistry. Basically, in an inorganic compound you have positive and negative ions, so it is better you first identify the nodes related to these positive ions, then nodes related to these negative ions. In that case, to analyze positive ions, you have cation analysis, then you have flame test, and you have D block chemistry. In separately, to identify negative ions, you have halogen, that means halide analysis, like I minus, Br minus, Cl minus. You analyze that separately, and furthermore you have some anions which give gases with water and with diluted acids and concentrated acid, and some anions which will give even gases with sodium hydroxide, and those things you can separately identify and learn. Then when you are learning about S and P block, again you don't try to learn S block separately and P block separately. Get the knowledge collective as a collective information. Then finally you will have a nice elaborative and collaborative knowledge. Right, so we'll move on to our subject. So why D block elements? So why these elements are called D block elements? This is not only related to D block, so S block, P block, D block, F block. So why? So what you need to consider is the final electron which is filled in the last sub energy level. So if that is a D block, that means if the final electron is filled in a D sub energy level, that means D block, you can consider that as a D block element. So that's the thing that you need to understand here. So then what are transition metals? So normally you know that you have several non-transition elements. So normally we say that zinc and scandium is non-transition. So why is that? So think about the stable oxidation states formed by these 3D and 4D elements basically. Then consider, is there any incompletely filled d orbitals? So if there are any incompletely filled d orbitals, then they are transition. We say they are transitions. And normally we say zinc and scandium, they are not that means they are not transition, they are non-transition. So why? So we will consider scandium, then zinc. So scandium, it is 4s2 3d1. So in scandium, the stable oxidation state that forms is scandium 3+. So it will be 4s0 and 3d0, and there is no electrons in the d orbital, so it is non-transition. Again, when you come to zinc is 4s2 3d10. So that means in zinc 2+, the stable oxidation state form, there is no s electrons, but the d orbital is completely filled there. So you can take either completely filled d orbital or empty d orbital. So if that is the case, they are non-transition. In between, incomplete ones, so they become transition. So that is the definition. Okay. Then you need to know some important general trends about 3D elements. Normally the boiling points, melting points, density, rigidity, conductivity. So I have given all the information here, so please go through that, and I am going to discuss few important from this, that is electrical conductivity. So now in a previous past paper question, they have asked the out of the 3D elements which will show highest electrical conductivity, and that is copper. So if you get the whole periodic table, so in 3D and 4D and some other metals, the maximum electrical conductivity is shown by silver. So that is what I have put silver and a question mark. So silver shows the maximum electrical conductivity, and in the same column you have all the three elements that shows the maximum electrical conductivity. Then about stability of coordination compounds. So this part is not much interested in your advanced level syllabus, but still you need to know some information about this. Now when you come to this stability, you need to understand the stability of a certain coordination complex depend on several factors like the type of the metal, the oxidation state, and the type of the ligand attached, coordination number, so several factors. So basically what you need to understand here is, if you have a certain metal given with several complexes given with the same oxidation state, you need to understand basically the stability primarily depends upon the electron donation, how this electron donation is given to the central metal and how back bonding is formed. So you might have not learned this back bonding concept in advanced level, so you don't need to consider that much. So understand the example that I have given. From the example you try to elaborate. So I have given some nickel complexes. So nickel bonded to 6 water, then 6 ammonia and nickel cyanide complex. So then stability increases towards the cyanide direction. So the main basic reason that you need to understand at your level is the electron donation ability of cyanides are normally very high. So in that case the stability also increases. So in this case, if I check the ligand, that means donation towards the metal nickel, water will have a minimum, then ammonia, then cyanide. So that is why the stability increases. So next we will discuss about the coordination number and geometry. So when you are writing a complex, normally we write a complex with a charge, or either we don't put the charge. So consider the example that I have given. So this is hexa aqua iron 2 complex. So I have not indicated the charge 2 plus, instead of that I have put Cl2 here. So one thing you need to understand here is hexa aqua with iron, that first part with the parenthesis, that is normally called the inner coordination sphere. And when you have the counter ion which is present to balance the charge, so we separately that the whole part is called the second, that means external coordination sphere. So basically when you want to get the coordination number, you need to get the number of ligands present in the inner coordination sphere. So in that case, here you have 6 water molecule coordinated to iron. So here the coordination number is 6, and if the coordination number is normally 6, we say that is octahedral in shape. So you have some tetrahedral molecules, tetrahedral complexes formed in this inorganic chemistry. So please try to remember that. Think about copper, then think about zinc. So think about those things. Then formation of colored complexes. So normally D block chemistry, in D block chemistry you have a lot of colored complexes. So these complexes, colored complexes, are normally formed because of the incompletely filled d orbitals. So in incompletely filled d orbitals, you have electrons that can show transition between the d orbitals. That means although you have 5 d orbitals, so that means dxy, dyz, dxz, then you have dx squared minus y squared, then dez squares. So these 5 orbitals are divided into 2 energy values. So one electron from the bottom can show transition to the upper one. That means normally the lower 3 energy levels you have, they are called T2G levels. In the above you have EG levels. So electrons can show transition and electrons can come back. So it will show some color. So that is what normally happens, but you need to understand this case is not always true, because if you get MnO4 minus, the color is purple, but consider about the oxidation state of manganese in that is +7. So +7 means the d orbital is completely empty. So in that case you need to understand that is not only the factor that determines the color. that means incompletely filled d orbitals. That statement is not always true. We should consider about some other factors as well, so think about that as well. Now in MnO4 minus case, manganese is +7, so there are no d electrons. So in that case you need to understand, you have oxygen bonded to manganese, so they have lone pairs, so these lone pairs can be added to the empty d orbitals, then they can show some transition. So we say that is ligand to metal transfer, charge transfer, so they can show some color. So example is titanium is purple, so why? So normally titanium 3 plus H2O complex, that is purple, so why? So think about that, why purple color, why it does not give another color? So basically what you need to understand is, in white light you have 7 colors in that rainbow, so some portion is absorbed by the metal complex and the other part is reflected. So we see the color purples, that means the energy values related to purple is reflected from the complex, so that is why we see these colors. So that sums up the introductory part of the D block chemistry. Then we have some important catalytic properties of D block elements. So this is very important because lot of D block elements are used as catalyst in many reactions. So I have given all these reactions based on a past paper question, so please understand the importance of this and please try to keep these things in mind. So I will go through few important things here. The first thing is vanadium. So you know that the contact process of preparing sulfuric acid, so in that case you know that to convert SO2 to SO3, you normally use vanadium pentoxide V2O5 as a catalyst. So I have given here platinum. So platinum is given because initially, that means before vanadium pentoxide is used, platinum is also used in another process to prepare sulfuric acid. And finally we have another reaction, that is C ammonia reacting with O2 and forming NO and 6H2O. So I have given a bracket and I have not filled there because I want you to remember this. What is this reaction? Where is this reaction comes? So think about the production of nitric acid. So this comes under that. So moving on, I have given some other uses of D block elements. So please scroll through this. Alloy, electroplating, battery, and we have an important that means use is about that means cobalt. So cobalt 60, it is used for cancer treatment. So you might have heard this before, so please make sure you know all the uses and catalytic properties of these D block elements, basically the 3D elements. Right, so we will move on to the chemical properties. So first I will discuss about scandium. So scandium normally forms this stable oxidation state +3. So again you need to write the electronic configuration of scandium and scandium 3+. So that is what I have put a space there. So when you are learning this, when you are taking notes, so please make sure you write the electronic configuration of scandium and scandium 3+ there. And when you are studying about other elements, so please try to write down the electronic configurations as well. Scandium, yeah, it is highly reactive, so it forms scandium hydroxides with water and releasing H2 gas. So normally we understand the concept with D block chemistry, they are forming coordination compounds with water like hexa aqua complexes, but scandium is little bit different because scandium reacts with water to form scandium hydroxide, like the sodium, that means S block elements, few X block elements react with water in the same way to produce hydroxide and hydrogen. So in the same way scandium also reacts with water. So this is an important thing that you need to know. So the other things about scandium is you don't need to know much about scandium because scandium 3+ is colorless, so you don't need it is normally not coming. A lot of things are not asked about scandium. So we'll move on to titanium. So titanium, you have several oxidation states, +2, +3, +4. So titanium and vanadium, Normally they are highly stable, that means generally stable, but at high temperatures it can form its oxide at highest oxidation state. So the example is given, TiO2, the oxidation state is +4. So think about that. And when you are considering vanadium, again read the last statement again. Vanadium is also forms V2O5 at its maximum oxidation state, that is +5. So understand this concept very well. So we will discuss about the compounds. So titanium with H2O, titanium 3 plus, it will form titanium H2O hexa aqua titanium 3 complex, that is purple in color. So you need to know this color. And titanium reacts with oxygen, nitrogen and carbon as well. So that is the basic thing that you need to know about titanium. And the important thing about titanium in the new syllabus is you have the titanium extraction in industrial chemistry, and titanium oxide as well, that means from rutile. So please make sure you go through that, that is very important. Then about vanadium. So vanadium you have +2, +3, +4 and +5. So titanium and vanadium are little bit very similar in their reactions, but you need to understand titanium does not show +5 oxidation state, but vanadium does show +5 oxidation state. So vanadium you have several complexes with different oxidation states, so make sure you know that. Vanadium 2+ complex is purple with water, that means hexa aqua complex. Vanadium 3+ is green, and vanadium 4+ is blue, and vanadium 5+ is yellow. So surely you need to keep these colors in mind. And about the oxides that I have given, please make sure you know the amphoteric oxides. That means if you consider oxides with lower oxidation values, they are normally basic. So if you consider higher oxidation values, they are normally acidic. So if you know the amphoteric oxide, for an example in this case, if you know VO2, which is the amphoteric oxide of vanadium and which is in the oxidation state +4, then you know that +5 oxide of vanadium should be acidic, and +3 and +2 of vanadium, that oxides should be basic. So that's the thing. So if you know the amphoteric oxide, basically that is normally enough. So for vanadium it is VO2. Moving on, chromium. This is another very important element. Show the +2, +3 and +6. So do not react with gases, but at some important condition, ambient temperatures, it reacts with oxygen, halogen and sulfur to form stable complexes which are in +3 oxidation state. So just know that. And chromium can form the chromium H2O6 2+ complex, so that is normally blue in color. But the important thing is in air it can be oxidized to its +2 to +3 oxidation state, so we can form the chromium H2O6 +3 complex, that is purple in color. Understand that. Then I have given important condition about chromium at acidic medium. Either you add its Cl or sulfuric acid. So make sure you know these things, because if you have normal chromium hexa aqua complex +3, it is normally purple in color. But if you add a acid, that means Cl or sulfuric acid, to make the medium acidic, now there will be no purple color, because the chloride complex and sulfate complex will be formed in that case, which will give a green color. And again, if you dilute the solution, the purple color will reappear. So that is the equilibrium reaction, so make sure you know that as well. In addition to that, chromium, it will form a dirty green color, precipitate with aqueous ammonia, little bit of aqueous ammonia or NaOH. So chromic hydroxide is that dirty green color. And if you add NaOH at an excessive level, it will form chromium OH6 3-. This is normally dark green in color. Okay. and if you add excess ammonia to chromium chromic hydroxide, you won't see this reaction. But you need to understand, in some cases chromium 3 plus tends to form a complex with ammonia. This is a special case, not that chromic hydroxide is added with ammonia, excess ammonia, and forming chromic ammonium complex. This is a special case where in some cases this chromium 3 plus forms a purple color complex with ammonia. This is a special case, please remember that. Okay. Right, so again, like the vanadium, so vanadium we have VO2 as the amphoteric oxide. So here we have Cr2O3 as the amphoteric oxide of chromium, that is in +3 oxidation state. So this is the basic things, these are the basic things about chromium. But you need to know furthermore about chromium, the important equilibrium reactions, the stability of chromate dichromate ions in acidic and basic medium. So first of all, we will discuss about the chromate dichromate equilibrium. Consider the oxidation state of chromium here. So dichromate or chromate, still the oxidation state is +6. So in water, this is present as the equilibrium that is given. Dichromate with water forms chromate and releases 2H+. So if you dissolve a compound like dichromate complex, that means dichromate compound in water, the orange color is formed. So if you add little bit of NaOH, you can see H+ can be removed from the NaOH in the above equilibrium, and the equilibrium, to maintain the equilibrium at a certain given temperature, the equilibrium will shift towards the right hand side, which favors the forward reaction, and chromate is formed. That means chromate is yellow in color, so a yellow solution is formed. So if you want to re-get the that means reappear this orange color, what you need to do is just add little amount of H+, that means acidify the medium, so orange color can be again formed. So chromate and dichromate, understand, it is in an equilibrium. So what will happen when you added a solution of barium chloride to a solution of dichromate? So according to that, if you add a barium 2+ solution, now barium 2+ can combine with chromate and form barium chromate. Basically this is yellow in color, and if barium chromate is formed, chromate is removed from this equilibrium, so again the equilibrium is shifted towards the right hand side and the medium becomes acidic. So this is very important. So these questions can be asked in MCQs, so please make sure you understand the concepts of equilibrium and you understand what will happen when a precipitate is formed. Right, so then about reactions of dichromate and chromate with H2O2. Now what will happen if you add H2O2 at acidic medium to dichromate? So what will happen here is, initially there is an orange color, so the color is due to dichromate. Then a blue color intermediate is formed. Then it is further converted to green in color. So what is the reactions that happen? What are the reactions that happen? So initially you have dichromate, that is orange in color, and with H2O2 and H+, it will form an unstable intermediate that is called CrO5. So I have given that reaction, the formation of the intermediate, so that is blue in color, and furthermore this CrO5 can be even reduced to chromium 3 plus, liberating O2. Now chromium 3 plus, it is you know that its color is green in color, so make sure you know these reactions. So dichromate, acidic medium, added H2O2, and it will reduce to chromium 3 plus with liberating O2. So the overall reaction is given at the bottom, so please make sure you know that, right? The other thing is, if you want to make chromate from chromium 3 plus, so these two are two different reactions which is a little bit interrelated. Now H2O2 in acidic medium to dichromate will form chromium 3 plus, liberating O2 as well. Now this is another reaction, H2O2 at basic medium to chromium 3 plus. Now this will convert chromium 3 plus to chromate ion. So in this case you need to understand a yellow color solution is formed, because chromium 3 plus is oxidized to chromate. In the above reaction, dichromate plus 6 is reduced to plus 3. So in the above reaction is a reduction. Now here it is an oxidation. So think about H2O2. What is happening to H2O2 at acidic medium to dichromate? So dichromate at acidic medium, you know that is reduced to chromium 3 plus. So H2O2 should oxidize. So you know that in H2O2 the oxidation state, that is -1, so it can be oxidized to O2. In the same way, in H2O2, in the latter process, that means H2O2 at basic medium to chromium 3 plus, so chromium 3 plus get oxidized, so H2O2 should be reduced, so -1 to -2, that is H2O2 to water. So these are very important equilibrium reactions. Then we will move on to manganese. So you know that in 3D elements, manganese will show us the maximum oxidation state, that is +7. So there are very important reactions of manganese as well. So manganese C, H2O6 complex is pale pink in color, and hydroxide is whitish pink. So in some case it is considered as white as well. So manganese hydroxide, so please understand it is oxidized in air to form MnO2. So MnO2 you might have seen that is black brown in color, so you need to know this reaction as well. So every reaction I have given you here is very important, so please make sure you go through this and you know all these reactions. And the other thing is manganese 2 plus with lead oxide and nitric, it will form lead sulfate, a white color precipitate, as well as HMnO4, that is a purple color solution. You have MnO4 minus there. And we need to discuss very important another important reaction. So if you have KMnO4, that is purple color in acidic medium, if you add little bit of KOH, what will happen here is it will be converted to MnO4 minus in green color, which is in green color. And if you add H2O2 for that, then it will reduce to MnO2, and if you add HCl, then it will form the Mn2 plus color solution. So I have given the reaction for that. So KMnO4 normally acidic medium, it is purple in color and it is little bit stable. So if you add base, then it is converted to K2MnO4, which is in green color, so liberating oxygen. So make sure you know all these three reactions. And K2MnO4 with H2O2, it will again form MnO2, then MnO2 reacting with HCl will form MnCl2, Cl2 and H2O. Now this reaction has been asked in several times in past papers, so that is why I wanted to discuss this. Okay. And the second thing is about MnO4 minus. Now you know that MnO4 minus basically stable at acidic condition, and if you supply basic condition, or that means you add little bit of KOH, now it will form K2MnO4. So what is about MnO4 minus? That means K2MnO4. K2MnO4 normally stabilized in basic medium, and when you make it acidic, now there is a nice disproportionation happening. So MnO4 minus, which is in green color at acidic medium, will be converted to MnO4 minus, which is purple in color with +7 oxidation state, and MnO2 black brown, that means dark brown in color, MnO2 is formed. Again, so if you can remember the amphoteric oxides, so vanadium we had VO2, chromium Cr2O3, and here again the amphoteric oxide, which is in brown color, that is MnO2. So basically we have discussed three amphoteric oxides, VO2, Cr2O3 and MnO2. So please make sure you know all these things. Right, so that is about manganese. So we'll move on to iron. So iron, it is normally oxidation states are +2 and +3. Those are the oxidation state that is possible normally. Then iron with dilute H2SO4 HCl, you know that hexaquion 2 complex is formed. So I have given two colors. Why is this? Because If you have high concentration of this complex, it is pale green in color, and if you have very poor concentration, a diluted solution, then we can see that as a colorless solution. But the problem here is this FeH2O62 plus can be oxidized using these given reagents. So when it is oxidized, it can form the +3 complex. So again, if it is very much concentrated, we see that as a brown or yellow brown solution. So if it is diluted, it is yellow like. Right, so then I have given the reactions of both Fe2 plus and Fe3 plus, so make sure you go that. So I will indicate the important reactions here. So if you add excess or either little bit of NaOH or ammonia to either Fe2 plus or Fe3 plus complex, please understand only the hydroxide is formed, because iron does not form complexes with either ammonia, or it does not dissolve with NaOH. That means excess, it will not form the anionic form. So the other important thing that you need to understand is the ferrous hydroxide green color can be oxidized to ferric hydroxide in air. That is an important reaction. And additionally, you have another important reaction, that is for Fe3 plus with thiocyanate forming the blood red complex. This is an identification reaction for Fe3 plus from Fe2 plus. So I have given all the other information, so please make sure you go through this. And the important thing about FeH2O63 plus is this is normally stable in acidic condition. So if the solution is not acidic, it can give H plus and form the complex that is given, which is normally a yellow brown solution. So this, due to presence of this equilibrium, we can say that iron is in two forms in media, in acidic or basic condition. The reason that I have included this reaction is this is asked in one of the past papers, so you need to understand and establish and know these things as well. Moving on, this is another important part, that you need to know the distinguishing reactions between Fe2 plus, that means identifying separately. So I have given the colors there. Then I have given the precipitates with the NaOH or ammonia there, and the important reactions comes after that. So you have potassium ferrocyanide, that is K3FeCN6. Identify the oxidation state, that is +T, that is ferri. And in the below third, that is ferro, that means you have ferrous. So you can identify 2 and C. So potassium ferrocyanide, if you add to +2, it will form a blue precipitate, and Fe3 plus will not give a precipitate. And ferrocyanide, Fe2 plus will have white and Fe3 plus blue. Okay. And H plus MnO4 minus and dichromate, so all these are oxidizing agents. So if you add to Fe2 plus, it will oxidize to Fe3 plus, and reagent, that means the agent will get reduced. So here MnO4 minus to Mn2 plus and dichromate to chromium 3 plus. But if you add that to Fe3 plus, you know that Fe3 plus cannot be further oxidized than Fe3 plus, so it will not show any color. And I minus with starch, so it will give a deep blue color, you know that. So if you have that means Fe3 plus solution, it can be reduced to Fe2 plus, and I minus can oxidize to I2, so that is why it forms. And the final reaction I have already discussed, that is the formation of the blood red complex from Fe3 plus. Furthermore, 8, 9 and 10, this is salicylic acid. It is given Fe2 plus will not form a complex, but Fe3 plus will give a nice purple color. This is a common reaction that we normally discuss in organic chemistry as well. So we try to identify phenolic compounds in organic chemistry. So for that we normally add neutral FeCl3, which will give a purple color. Now this is the case. Now neutral FeCl3, you have Fe3 plus. So Fe3 plus with phenolic compounds like salicylic or other phenols, it will give a purple color. Now this is the common reaction. Then H2 is at acidic medium. So Fe2 plus cannot form, because Fe2 plus need a basic medium, because its KSP value is very high. So But Fe3 plus, it can show oxidation reduction reactions to form sulfur. Then ammonium sulfide, make sure you know that FeS precipitate is formed. That means sulfide is there here, ammonia is making the solution basic, so it can form, but Fe3 plus does not have any reaction. So I have given a few important, that means 10 important reactions to identify this Fe2 plus from Fe3 plus. So please make sure you go through this. This is very important. Moving on, cobalt 27, very important. So H2O6 complex is pink, and I have given some important reactions of cobalt as well. So cobalt hexaqua complex is pink, but if you add concentrated Cl minus, that means excessive, this is, or Cl minus concentrated or excessive, it will form COCl42 minus, which is in blue color. So this is commonly asked in exams. Then H2S under basic medium, it will form the black color precipitate copper sulfide. And the important thing is NaOH with cobalt hexaqua, it will form cobalt hydroxide, which is also in blue color. And important thing is cobalt can form the amine complex. So we have learned few: scandium, titanium, vanadium, chromium, manganese, iron. So all these metals normally they do not form amine complexes, except the fact that chromium can form a special amine case. So special amine, that means chromium H263 plus. And here in this case cobalt, so it can form cobalt hexamine cobalt 2 plus, which is yellow brown in color, and it can oxidize to 3 plus very quickly in air as well to form the orange brown complex cobalt hexamine, that means 3 plus complex can be formed. So make sure you know that. So this is also very important. Right, so nickel and copper. What is important here? Nickel and copper, you need to understand. Nickel forms a hexaqua complex at +2 state, which is greenish in color. So not completely greenish. In some cases you can see that as greenish blue. So green or greenish blue. In copper it is the other way around, bluish green. That means blue, it is more towards the blue or pale blue color. Nickel more towards the green in color. So its hydroxide is a little bit different. Nickel hydroxide is green, copper hydroxide is blue. And the important reaction of nickel is it will form the nickel hexaamine complex, that is deep blue in color. And for copper 2 plus, it will form the tetraamine complex, which is also in deep blue color. So identify that. Okay. Now, if that is the case, so how do you identify these two nickel if you have the hexaamine complexes? The easiest way is copper with H2S either in acidic, neutral or basic medium, it will form copper sulfide black precipitate. But with nickel, you need to have this neutral or basic medium to form the nickel sulfide complex. So that is the reaction that you can separate this copper 2 plus and nickel. Basically that is okay. So we'll move on to important reactions of nickel. So nickel hydroxide is formed, amine complex is formed. Yeah, that is okay. You should know the other reactions as well I have given. And the important reaction is nickel DMG. So nickel can form nickel DMG complex, that is red precipitate, nice red precipitate. And the important thing that you need to know is copper 2 oxide and copper 1 oxide. So I have given, see, if you heat copper hydroxide, you can have copper oxide CuO, which is black in color. And the other thing is, if you have copper 2 plus, you might have remember this failing solution when you are testing for carbohydrates. So it can reduce to Cu2O, which is a brick red precipitate. And finally the important reaction is copper 2 plus when you are adding HCl. That means if you add little amount of Cl minus, it will form CuCl H2O5 plus complex, which is green in color. and if you add furthermore Cl minus, it will form CuCl42 minus, which is yellow green in color. Now this reaction is very important because in one of the past papers again this reaction is asked, so it is better if you know these reactions as well. So moving on, again we need to consider the reactions which we can distinguish between copper 2 plus and nickel 2 plus as Fe2 plus and Fe3 plus. So copper 2 plus, I have given the important reactions here. So I am going to explain the HCl H2S case and NH4H NH4Cl H2S case. So you can see copper at acidic condition or basic condition, copper sulfide is automatically formed. But for nickel, you can see that at HCl condition, HCl H2S, the precipitate is not formed. But in ammonium hydroxide, ammonium chloride condition, that nickel sulfide is formed. So why is that considered? So I will explain the reason as well. The reason is the precipitates are formed basically due to the solubility product values at a given temperature. Now in acidic medium, the H2S gas that is in equilibrium as H2S giving HS minus plus H plus, then again there is another equilibrium, HS minus giving S2 minus and H plus. So S2 minus is the part that forms the precipitate. If the medium is acidic, that means there are a lot of H plus ions. So this equilibrium, both equilibrium will be shifted more towards the left hand side, and there will be a very poor concentration of S2 minus. So in acidic medium, you will have a poor S2 minus concentration, and in basic medium, you have a higher S2 minus concentration. So the precipitate which will form at either acidic condition with low S2 minus concentration should have lower Ksp values, because you know that the RQ or the ionic product of a certain precipitate, partially soluble precipitate. So if the ionic product passes the solubility product, then it will precipitate. So in that case, if the solubility product of a certain precipitate is very low, then it can quickly pass the solubility product. That means ionic product can quickly pass the solubility product. So in this case, you need to understand in group 2 analysis, if you can remember, we have 9 precipitate actually. So in that case, you need to understand all those precipitates have very small Ksp values. That is why they are precipitating, because at acidic condition S2 minus concentration is very small. But in basic condition, you know that the S2 minus concentration is very high. That means in basic conditions, the precipitates are the soluble products are very high. That is why they get precipitate, because they have a lot of sulfide concentration. So that is the reason. So we will move on to some other important elements. So finally we have zinc. So about zinc, so you know that zinc is amphoteric. So zinc can react with either dilute NaOH to form Na2ZnO2 and H2 gas, or either dilute sulfuric to form zinc 2 plus aqueous, that is colorless. So then I have given how zinc reacts with NaOH or ammonia. So it will form the zinc hydroxide white color precipitate, and it can form the either amine complex, zinc tetraamine, or either zinc OH42 minus with excess OH minus. So normally when you are learning these amine complexes, we have basically 2 amine complex which will form tetraamine complex. One is copper 2 plus, which is the blue in color, and zinc amine complex, which is colorless in color. Then I have given the important reactions of zinc hydroxide and zinc oxide. So remember about zinc oxide, because zinc oxide is very important in identification. In some reactions they have given these statements, and finally they will give this one. This oxide is formed, and this oxide is yellow in color, little bit yellow in color at high temperatures, and when the temperature drops and it turns white. So this is zinc oxide. You need to identify from that. Okay, so this sum up our 3D elements. So normally when you are learning D block, you only learn up to this 3D elements, but apart from these 3D elements, you need to know some other important metals as well. So I have given some other important metals here. First one is silver. So what are the important reactions of silver? So silver chromate, brick red in color. This is asked in some questions. And Ag2O, make sure you know the color. Ag2O, that is brown, and Ag2S, that is black. Then what is the color of AgCl? So AgCl, you know that is a group 1 precipitate, that is white in color, and if you add ammonia, it will form the diamine silver complex, that is colorless. So I think you can remember when you are preparing the tolerance reagent, so you should know all these reactions as well. So moving on, we have what is that, antimony and bismuth. So this reaction is very important. You know that in cation analysis in group 2, when H2S is added an acidic medium, Sp2S3, which is in orange in color, and bismuth sulfide, which is black in color, is formed. And the reaction that is given on the right hand side is very important, because if you add HCl to a solution of Sp3 plus and Bi3 plus, and then if you dilute the solution, you have a nice white color precipitate, BiOCl or SbOCl. It should be BiOCl or SbOCl. This is an identification reaction for either bismuth or antimony. So this is also very important. That is what I have. That is why I have given here. Moving on, we have other two separate metals, that is cadmium and lead. So cadmium, again, understand it is very much similar to zinc 2 plus as well. Cadmium just below zinc, so it is very much similar. So the important reactions is cadmium also can form the amine complex with ammonia, that is you should know, like the zinc tetraamine complex. And cadmium with H plus H2S, it can form CDS, which is yellow in color. And then about lead. So lead, I have given some important reactions. So lead, again, PbCl2, I think you can remember, that is white in color, but dissolves in hot water, and when you cool it again, the precipitate reappears. Lead sulfate is formed, that is white in color. Then lead hydroxide with NaOH and excess NaOH, it will form PbOH42 minus. So what about the lead 2 plus with ammonia? So if you add little bit ammonia, again lead hydroxide is formed. Excess ammonia, no lead amine complex is formed. So that's all. So I have given some important information. So PbCl2, like PbCl2, you have PbBr2, which is a cream color precipitate, which dissolves in hot water again, and PbI2, which is a yellow precipitate, and when it will also dissolve in hot water, and when you cool it, then you can see like gold dust. You might have done this, or you might have seen this. So if you have not done this, please make sure at least you look a video about this gold dust formation. It is really nice. It is like actually like gold. So please make sure you go through this. So this sum up our lesson for today. So I have been discussing about D block chemistry. So basically I have given the information about 3D elements, and apart from that I have discussed about silver, bismuth, antimony, cadmium and lead, which is very important in your cation analysis or cation chemistry, that means positive ion chemistry. So I hope you like this video, and please subscribe to my channel. And in coming videos I will upload some other important about inorganic chemistry, further about the anion analysis as well. So thank you very much.